Hi everyone, today our project topic is parallel computation model. A big challenge in parallel computing is we don't have a single model that everyone uses. In regular computing, we have the RAM model. This model helps us create algorithms, design computers, and make programming language effectively. In parallel computing, where many tasks happen at the same time, we don't have a similar model. This is a problem because it makes it harder for us to work together and use multiple processors. Why does it matter? If we have one model for parallel computing, like the RAM model, it will make our work much better. It will help researchers and developers work together more smoothly, speed up new technology, and improve process in many industry. So our goal should be develop a standard model for parallel computing that support this kind of teamwork and efficiency. These are the different types of parallel computation models. First, we have the PREM model, an extension of RAM used for single processors. Introduced in 1978, PREM allowed multiple processors to access a shared memory at uniform speed without needing synchronization instructions. Despite its simplicity, which aid in creating parallel algorithms, PREM falls short in practical application due to its disregard for real-world complexity, such as memory access, delays, and synchronization issue. Moving to the BSP model, it is structured around superstep that include individual computation, communication, and synchronization. This model excels in systems with distributed memory and is relatively independent of hardware. However, its assumption of perfect synchronization and fixed interval can be impractical, limiting its use in scenario where dynamic flexibility is needed. The log-P model, on the other hand, introduced more granularity by accounting for latency, overhead, gap, and the number of processors. It aimed to provide a more realistic depiction by considering communication delays and the processing overhead, which are critical in actual systems. Yet, it often simplified the complexity of real environment by assuming constant parameter. Lastly, our proposed model, EHBSP, built on the existing BSP framework, but specifically target the overhead involved in divide and conquer strategy, like those used in QuickSort and merge-sort. It integrates dynamic task creation and synchronization, making it particularly effective for complex parallel computations in distributed systems. Our experimental setup. Our tests were conducted on the CIMS compute server. And this server has four AMD Alproms, and it was running at 2.1 gigahertz with a total of 64 cores. And we implement three key types of algorithm: sorting, searching, matrix. For sorting, we implement QuickSort and merge-sort for different number of input array. Search, we implement the binary search. For matrix operation, we implement using two different algorithms. For implementation, we use programming language C and OpenMP for managing the parallelization. We test each algorithm using 1, 2, 4, and 8 threads to see how performance change with the number of threads.
For the results, we use the QuickSort to analyze and measure the metrics. And for the first figure, you can see that for smaller input size, increasing the number of threads didn't show significant performance improvement. Sometimes it even takes longer execution time. This is normal since the more threads we have in small problem size, more overhead may occur. And as we scale up our problem size, the scenario flips. The time taken decreases, notably as we introduce more threads into it. And for the speed up analysis, we end at 1,000, increasing threads seem to diminish speed up, which is reasonable due to overhead. Yet when we take on more extensive data sets, the speed up improves a lot, particularly when 8 threads are employed. a speed of about 6 times compared to a single thread execution. The improvement from parallelism is depend on the problem size. As you can see that the larger data sets, the better improvement from the number of threads. Finally, let's consider efficiency. Across all problem size, the efficiency trend dips as more threads are introduced. However, the drop is most obvious when with the smallest problem size. This again suggests a misalignment of resource to workload. And in contrast, at n equaling 10 millions, the efficiency retains at pretty good levels even at higher threads counts, hovering around about 0.8 with 8 threads. This efficiency ratio is indicative of more considerate application of our computational resource, leveraging them to fullest when faced with the demands of massive data sets. From this result, we can know that our implementation works pretty well. In our project, we compare 3 different models. PRAM is the first, and it assumes we have unlimited processing power, but our results show that this isn't quite realistic because it doesn't take into account the latency. And for the log-P model, this model considers the delays in passing message around. Our experience with QuickSort supports this. Adding more threads means more coordination is needed, which adds to the time taken. But we can still notice that there are still hidden costs showing up as we add more threads. This leads us to our proposed HBSP model, which adds even more detail by looking at the cost of breaking down a big task into smaller chunks. In short, HBSP is about knowing when to ask for more threads or when to streamline the process for the task. By managing data movement and reducing unnecessary action, we make sure our computation work is as effective and efficient as possible. We have seen that the gains from parallelizing QuickSort, while beneficial for tackling large problems, aren't as good as we once thought. This brings us to an important realization. Factors like how our computers communicate with each other and stay in sync cannot be ignored. They are the essentials of the parallel computation and play an important role in how well our algorithms run. This is where the HBSP model steps into. It fine-tunes the HBSP framework, addressing the details that can cause hiccups in divide and conquer algorithm like QuickSort, with its strategies for profiling overheads and synchronizing more effectively. HBSP allows us to peek under the hood and get a clearer picture of what's happening at every level as our computational hierarchy. That's all from us. Thank you.